Hi everyone, we are here again. I'm in the same outfit that I was in the previous videos. I'm trying to record a couple today, or a few today, then I'll do a few tomorrow, a few the next day, so they're all ready for you guys when class starts in a few weeks. But my feet are already hurting, so I'm not going to be doing, this will probably be my last one, looking in this outfit, Okay, so we're going to be doing what is science and positivism. So if you're following along in the PowerPoint, whether you have like a side-by-side on your laptop, whether you want to just hear my voice and then you have the PowerPoint in full screen, I trust you guys to find the way that works best for you. Everyone's going to have their own strategy of what works best, and the convenience of the recording. The lectures being recorded is that you can pause, you can rewind, So like I said before, I will move a little quickly just so we can, keep these kind of short and sweet. And then but you can rewind them and go back and listen, all that stuff. Okay. So what is science? So the first slide, what exactly is science? So in a general sense, this is how we gain knowledge about the world around us. That's a very general explanation, right? Because there are plenty of ways where you can gain knowledge about the world around you. Science is just one of those ways, right? But there's more to science than just, making a hypothesis or something. There's a whole process, not even just the scientific method, even more beyond that. So we're going to talk about that today. You'll see that this PowerPoint's kind of short, so hopefully I'm not jinxing myself when saying hopefully the recording will also be a little bit shorter. Like I said before, I want to keep these not overwhelming you guys, with really long-winded lectures. So if you're looking at this first slide, you'll see this funny meme from The Simpsons, and I think it's the principal, right? He's saying to Bart, there's nothing more exciting than science. You get all the fun of sitting still, being quiet, writing down numbers, paying attention. Science has it all. It's true. I literally, I've been working on my dissertation. I'm at the end, and it's crunch time, right? All I've been doing, what I've been doing every day is sitting at a computer, looking at Excel, running a bunch of stuff, stats, making charts, so. But it's still cool. Like, I'm a scientist, and I've done this amazing research, and now I get to formulate it and analyze it, and then I get to describe it and discuss it with my colleagues. It's actually I think it's a very enjoyable experience being in a science field. Okay, next slide. So starting off with the scientific method, right? So here we have the first two steps in the scientific method. Now, depending on where you learn the scientific method, it might have, like repeat as a step. Like I only have 4 listed. That's totally fine. So we've got observation. So literally, the first thing, before you can have a hypothesis, before you can do any research, you have to have observed something, right? With your senses. You saw something, you smelled something, you heard something, and it made you curious. You were like, I wonder why that happens, or I wonder what that is. And then you create, step number 2, you create a hypothesis based on that. Now, your hypothesis is usually based on the very limited information that you have within your observation. You notice something interesting occur, like I said, you saw it, you smelled it, you heard it, and you come up with an idea based on just your very limited information. As a way to kind of explain that, like, let me see, this is the explanation I think will work, and then you can then test that, right? So then moving on to the next slide, you'll see the next 2, step 3 and 4. Step 3, experimentation, and that's going to be different depending on what science you're in. You could be in the lab with chemicals. You could be doing a questionnaire and survey with a bunch of people and creating a large data set for their answers. You could be, like myself, using CT scans and collecting, morphological data from the CT scan. So it's going to be your experimental stage or your data collection stage is going to be different depending on which field you're in. And then at the end, step 4, conclusion. So this is when you're going to analyze, your data. And then you're going to either accept your hypothesis or reject it. And just to be clear, it's accepting or rejecting. I think that there's a misunderstanding that, you always want to be able to say, my hypothesis was correct. But sometimes it's more interesting when you were wrong, because you might be thinking, this is so easy to explain. Here's my hypothesis. It's probably right. The data are just going to back this up. And then you're like, whoa, I was totally wrong. Sometimes that in itself is like, there's something weird going on, right? So rejecting or not rejecting, totally fine. So that's like this, like I said, the scientific method. We've all heard that. We've had versions of that we learned in like elementary school or junior high or high school, right? But that's kind of the very basics of you observe something, you create an idea that might explain it, you have a data collection process, experimentation process, and then ideally, you would do some kind of statistical analysis to confirm, because we don't want to just use like our human eye, our flawed human eye, to be able to say, oh, I see this trend or this pattern. Like as an example, let's say I had a bunch of skulls laid out on a table, and I was like, hey, what are things you notice about, let's say, a trend? Do you see, skulls going from small to large? Do you see the eyes getting smaller as you go from, first skull to skull number 5? Like, what are some trends you're seeing with your human eye? Now, you might pick up on a couple things, like, oh, yeah, the heads seem to be getting bigger as you go from one skull to the next to the next. Well, then if you actually examine that statistically, you might find, oh, your eye was picking up on something that really wasn't there. And then the opposite can be true. Let's say you're like, I don't really notice any trends or patterns with the eyes, but then you actually collect data and you run some statistical analyses and you realize, whoa, there was actually an interesting, shape change in the eye orbit that I wasn't even picking up on with my human eye, that now, because we have this process of the scientific method to confirm it usually with statistical analyses, that's, an unbiased approach. So you're getting like truthful, factual information at the end of this, right? That's kind of the whole point of this whole thing, right? So now the next slide, though, what are some other things built into the scientific process? It's not just, scientific method and done, right? So there are other things. Sorry, I'm thirsty. So I have the bullet pointed list here. We've got the positivist paradigm, rules of objectivity, and then peer review. So the next slides will talk about this. So next one. Positivism. You have this nice list of what does positivism mean. So maybe you have heard of a word called a paradigm. A paradigm is like a perspective. So typically we have very like clear paradigms within any scientific field or any field in general that you might work in. Or you could have a life paradigm. This is the way I perceive things, the lens through which I view my life experiences, or the lens through which we, conduct research. So basically that's what a paradigm is. And in pretty much every science, we use what's called the positivist paradigm. So positivism basically is, and like I said, you could see this on the PowerPoint if you're following along, some general premises built into this concept. So the first is that this is reality, right? We all exist in reality together. And you might be thinking, oh, well, of course, but there could be other approaches where you would say, oh, we're all in a dream, or like something like that, right? There are plenty of other paradigms where that might be the approach. In the positivist paradigm, that's not the approach. We all agree, kind of built, before we do anything, it's like, okay, we're all agreeing that we all live in the same, there is a reality, it's here, we're in it, we exist in the same reality, we're all experiencing things the same way, And then kind of going through this list, we can learn things about this reality, like we can measure things, we can gain knowledge from those measurements. Like if, say, there's a table in front of me, I can measure that table with, my ruler. You can then take the same ruler and then measure that table. We will get the same answer, like if you're, not just being lazy about it. You know what I mean? But like our reality is knowable and measurable. And that's kind of the whole idea of science, right? If our reality was all a dream, or if we couldn't measure it, or it wasn't knowable, then science would be useless. You know what I mean? There would be no point in measuring something if what I measure is just in my head, or you know what I mean? Uniformity in space and time. So the laws and rules that kind of govern the processes of our reality, like evolution, gravity, whatever it is, those, it doesn't matter if it was today or 10 years ago or 200 years ago, those same processes of, they still apply. And then whether I'm in this location or another location, they all, still apply, that idea. Natural causality, so cause and effect, right? This is a big one. So as a positivist, we would say that if something happens in this reality, it is caused by something else in this reality. Now, you could have a personal opinion that you might think, well, some things that happen in this reality are maybe caused by something in another reality, like maybe like a supernatural reality. You might even be right. There's just no way to examine that from a scientific perspective, right? So using positivism, we would say cause and effect is all about this reality. It's all about this reality. It's not saying other realities don't exist. It's saying that's just not what we're doing right now. That's not part of it's not part of this. It's not part of science, right? And then, of course, in science, we want to remain objective versus subjective. So subjective would be like personal opinion, personal experience, and there could be value in someone's personal experience for sure. But if in terms of a scientific endeavor, that's not really important, right? That's just it's anecdotal. So you want to have as much as you can, and that's why this process will kind of weed these things out, these biases out. You want unbiased, truthful, factual information. So when you start with just your simple observation to this whole process of maybe doing research, at the end you get as close to factual and unbiased and truthful information as is reasonable for us as humans. That we've created this great system where at the end result will be the closest we can get to that. And then, like I mentioned before about statistics, you want to make sure you're backing up your ideas with some kind of statistical analyses to say, look, math is math. Math doesn't care about your opinion. The numbers don't care whether you feel this way or this way. Like, the numbers are just the numbers. So you're going to get factual, unbiased information from that. You might not even be doing it on purpose. It's not even like, oh, you're a scientist who's trying to, make your research say what you want. It could just be, we have different methods we come up with all the time that we realize, oh, this method works better for us now versus the method that we used 30 years ago. Like, science is always shifting and changing, and this is part of the process too. We're always, building upon itself. And also the last one on this list is the use of reductionism. So simply put, reductionism is you might be looking at a really complex phenomenon. You've observed something that's got a lot of factors involved, and you're like, how do I kind of parse all this out to get to like the heart of the matter for whatever you're observing? Sometimes what we call like reducing it to the most basic factors. Like, instead of looking at all 20 factors, you're looking at, okay, what are these 2 factors that are kind of at the basis of this whole thing? Let's just take out the fluff, right, and look at these kind of other factors. You could say, well, those other factors are important, yes. And this would just be how you approach your research, how you would write up your research. Like, you might say in your limitation section, you could say, we decided to eliminate XYZ as a factor to kind of see what we get in terms of what we're looking at, with just kind of this reductionist view. Then later on with another experiment, data collection process, you might decide to pull in some of those other factors to kind of see, like, that's kind of the way science works as well. Next slide. Objectivity. 3 main things here. Science has to be repeatable, it has to be falsifiable, and it has to change with new evidence. So not all ways of gaining knowledge about the world, this might be the case, right? You could have a way of learning things about the world where it doesn't change with new evidence. You might have a system of knowledge where you're like, I know this thing and no evidence can make me change my mind about that. You're allowed to do that. That's just not science, right? There's something wrong with another way of doing something. There's no value judgment placed on whether you have the scientific paradigm, another paradigm, right? They're just different. But in science, right, so repeatable. Repeatable means like someone else needs to be able to come along and do my research or someone else's research. It can't be something hidden, right? So for my master's research, very briefly, I'll describe it. So I looked at the choice to remain child-free for females between the ages of 18 and 50. And I looked at this from an evolutionary perspective. And I had like this really complex, well, not super complex, moderately complex medical survey that they had to do if they wanted to participate, or to ask them questions about their medical history, their family's medical history, their choices in reproduction, right? And then I took all of those data and then I put them in a spreadsheet and I, ran some statistics with them. But someone else needs to be able to like read my, my thesis and say, oh, I'm going to try to do that same experiment, but I think I might shift the age range a little bit. Or I see that she did that experiment only in this one location called Sacramento, California. I think I might try another location and see if the results are similar or are they different, right? So being able to repeat something is very important. It can't just be, oh, I wrote a thesis and I'm like, oh, I have secrets about how I did my research. You can't know them. But everyone's going to be like, well, how do we know you didn't just fake it, right? So you have to be very open with your research. Other people need to be able to repeat it to show that it's accurate. And just in general, repeating even your own. So let's say, as an example, you are going to the doctor and the doctor wants to put you on a new medication. And he says, hey, there are 2 medication options. One there's been 2 studies shown that this works really well, and for this other medication, there's been 15 studies that show that this works well. You're going to probably be more relaxed and more trustworthy of the one that there's been more research, right? So that's just repeating itself. They're going to do more research, repeating the same research. You want to make sure that what you're getting the same results time and time again. Because if you just do one research study, and you're like, that's it, and no one else ever comes along and retests that or takes a look at it or critiques maybe your method or something, then there's no way to really know was this really, that information, is that factual or not, because you need to be able to repeat it in science. The next one, falsifiability. Falsifiability means there has to be the ability for you to be wrong. So just like we talked about with the hypotheses, either you reject your hypothesis or you do not reject your hypothesis, right? So it can't just be that whatever you get at the end of your stats, you're like, oh, that fits in with my idea, right? There has to be, we call this hypothesis-driven research. So you're like, here's my idea, I think this is the explanation. And then your research, you run your stats, you're like, oh, I can accept my hypothesis. Oh, I can, reject, or not, I shouldn't say accept, not reject or reject my hypothesis. There has to be the ability to do that. It can't just be, oh, I ran my stats and, oh, this all kind of works with whatever my idea was, right? That's not really good science at all, right? So you want to make sure that you can you want to make sure that in your research, whatever you get at the end, your conclusion, that there is the ability for you to be wrong about your hypothesis. You might not be, you might be totally correct, but there has to be the ability built into how you do your research that you could be right or you could be wrong. It's very important. And then number 3, changing with new evidence. All the time in this world, we get new technologies, new methodologies, new perspective, new ways of thinking of things. And we, as a science, we're open to all of that, right? We could have said, 50 years ago, we know everything we need to know about whatever, anything, right? Biology, anatomy. And we would have missed out on decades and decades of new research and new technologies and, new scanning types and, you know what I mean? So changing with new evidence is very important. Not every way you gain knowledge about the world around you allows you to change with new evidence. You might have a way of being in the world where you're like, this is this knowledge, and here it is right here, and no evidence that comes along is going to change that for me. You're allowed to have that, but science just doesn't do it that way. We do it very specifically in a very different way. The next slide, peer review. So there's an image here. This is so accurate. So I've had to do a peer review process when I submitted grants to the National Science Foundation, and it's kind of like this meme. The first reviewer is like, oh, this looks fine. The second reviewer is barely paying attention. And then the third reviewer tears your application or whatever it is, your thesis, article, whatever it is, tears it apart. Basically, the reason we have peer review is, let's say you have observed something interesting in the world. Then you went through the steps of the scientific method. Then you made sure that you were objective, how you've set up your research is repeatable and falsifiable. You're keeping to the ideas of positivism and cause and effect in this reality, all of that you're keeping in mind, right? And so then you get this great research at the end. You're like, here's my conclusion. Now to even weed out even a little bit of bias that might still be there, you present this information to others who are also experts in your field. Now, how we do this today is typically, let's say you're a faculty, at a university, right? Usually part of your job description is that you have to be a member of certain journals, scientific journals, and so throughout the year you're going to get a handful of different articles it's all going to be anonymous, right? Well, it's supposed to be, but because basically you're sent different articles to critique, maybe 2 or 3, it depends on the university, it depends on what science journal you're doing it for. And you're going to just anonymously, they're anonymous, you're anonymous, you're going to critique this, right? And it's going to be stuff that's in your particular field. So it's supposed to be all anonymous, but you might say, as you're reading, I recognize this style of writing, that's probably, Dr. X or whatever. So it's supposed to be anonymous, but every once in a while you can imagine that it might not be. But and also you can set up hey, I have this weird academic rivalry with, Dr. G. Can I just make sure that Dr. G never gets any of my stuff to critique? And usually the journals will say, oh, that's probably fine. That's not a problem. So that can happen, right? But so then you have other experts in your field reviewing, their hypothesis, their methodology, what stats did they use, and kind of like the meme shows, you might have one reviewer that's like, this is really great, you did a great job, I would maybe, add a little bit of this, a little bit of that, but it looks great. You might have a second reviewer kind of saying something similar, like, oh, this is fine, I really wouldn't change a thing, or maybe a couple little tweaks, maybe a couple grammar, tweaks they have for you, and then you get this, typically, sometimes not always, you get at least one of the reviewers who really critiques it, and it can be a little like, you're like, oh, I'm so tired, I just want to be done with this project, but it's really good for the science, right, that you have someone who's also an expert in your field who is saying, hey, look, this method you used is great, but there's kind of this new method. Maybe you should try using that. Or maybe you weren't aware, but we don't even really use that method anymore. This is the one that most of us use in our field. Or your theoretical perspective, I think you should use this approach. We're using this approach. That can happen sometimes. And then you could say, well, I use this approach. You don't. That's fine. And then you could just, in your revisions, once you typically resubmit it, to the journal, you can say, hey, I made adjustments per all of my reviewers except, this one, because I feel like, the reviewer and I just don't see eye to eye on this, and here's the reasons why I think I should keep this. There's a back and forth process to this, but at the end, the idea is that you have had other experts in your field critique what you have done, and so at the end of it, you have this, this packet of information that is as free from bias as possible. It's objective information. It's factual, objective information. The next few slides are just some funny examples of scientific papers, like titles, right? Let's see, there's a couple funny ones in here. My colleague is wrong, and I can finally prove it. This is so true. So I remember I was taking a seminar, maybe in my first year of my PhD program. It was on like a professional ethics or something. So we had a handful of different topics we talked about, and for one of the assignments, we had to map our academic family tree. Basically, like, who is your advisor? That's your academic parent. Any other graduate students they have are your academic siblings. Whoever was your advisor's advisor is your academic grandparent. And what you will often find is, if you go back further enough, there might have been, let's say, the great grandparent. They had a handful of graduate students, right? And then they all kind of went separate ways, and so like anyone in their different lineages, they don't get along, or not in like a true way, but like they might just have a lot of back and forth in terms of the research and different articles they write. And sometimes it's really subtle. There was this one example our instructor gave us. Gosh, it's been years, but it was like these titles of these articles, and they were very subtle, but it was something like they were working on the same idea. And one of them, the article was like, the definitive study on, ABC. And then the other person who, if you didn't really know, there was this kind of academic rivalry you might not have noticed, but then their article that they wrote, 6 months later was like, the true final definitive study on ABC, So it's just interesting back and forth. It's funny, but it's true. Let's see, next slide. Some thoughts on how everyone else is bad at research. We see these every once in a while. It's always good to have a critique, Let's see. Oh, this first one. The task I had to do anyway turned out to be hard enough for its own paper. That's true sometimes. Oh, this happened to me a few times when I'm doing a poster. Like, okay, I'm going to do a presentation at a conference. I'm going to make a poster. I'm going to pull some of the data I've collected for my project. I'm going to pull like part of the data. I'm going to ask a simple question just so I can make a cool poster. And then you're like, oh, wow, well, I'm going to ask this question, then I should probably ask this question. And then suddenly it becomes multiple things, even though you're dealing with just like a subset of your data. So you can get carried away. It's very easy to do that. There's other ones, but I'll move on. So then academic translator, these are funny. So what academics say versus what they really mean. So you might say various sources. In reality, you mean, I forgot the name and author of that one paper. This is so true. This is so true. There have been times where I'm like, what was that article I read 4 years ago in that one class? I think the guy's name last name starts with a B, and you're just like trying to find it, Let's see. We are grateful to the 2 anonymous peer reviewers for their constructive comments, and what they actually mean is, God help them if I ever find out who they are. Oh God. Let me go down a few. This one is an extensive literature review is actually, A quick Google search. This is making us sound bad. It's not. It's just we're human, right? These are funny. Here. It is impossible to summarize simply means I still don't understand. There are different ways that you can word things when you're writing a paper for, a class or a conference or whatever, where you can be, what's the word I'm thinking of? You can still, even if, let's say you're like, oh, this article, or I'm sorry, this research study didn't really turn out the way I thought, or there are ways, like I kind of said before, there are ways to still be positive about that, and especially in the way you describe it. And it's true. You're not like lying. It's totally true. You could say, look, I had to reject my hypothesis, but this is interesting because of blah blah blah, and I really think now this is kind of going to lead us into a whole new realm of investigation. Like, there are ways of framing what you're doing, keeping it professional, and keeping it positive. And you just have to, like, as you continue in your academic career, you're going to get really good at, like, if you decide to, you're going to get really good at how you describe things, how your writing is, you know what I mean? So you might have something that you want to say that's a little, you're like, oh, this didn't really turn out the way I wanted it to, but you don't really want to say that, right? Because that's just like, that's negative. You want to frame it in a way of, like a really good scientist would say, this is going to lead us into something else possibly, or this did not turn out the way we thought, but that's actually really interesting because of, X, Y, Z. So there are ways of, and this is really just like your mentality as a person, your mentality as a scientist, right? Okay. Oh, the next slide. Let me take another sip of my. Scientific theory. This one is very important. In fact, if you take only like 3 things away from this class, this should be one of them. The word theory, the way we use it in everyday conversation, is not the way we use it in science. In fact, there's a lot of terminology that we use in science that if you use like the equivalent that you would say like in everyday conversation, they're not going to be the same, right? And this can sometimes cause confusion. And a really good example of this is the word theory. In like everyday conversation, you might say, oh, hey, are you watching that new show? I have a theory about who the killer is, right? Basically what you're saying is, I have a general idea, and might even be based on a little bit of information. In science, the equivalent of that would be hypothesis, right? It's a good guess based on maybe a little bit of information. The term theory in everyday conversation means, it's a good guess, maybe there's some validity to it, probably not too much. You really have to take it a step further. In science, however, the term theory, that's not what it means. It actually means something completely different at a much higher level. In science, the word theory means that over time, different universities, different labs, different probably subfields, research has been accumulating that is showing this one phenomenon, this one large explanation to be this overarching explanation for what we're kind of seeing as a process. So there might be little laws and rules that will describe, smaller phenomena that might describe very specific scenarios, but once you start combining all those little laws and rules together, you get a theoretical perspective, you get a theory, right? And so a theory is the pinnacle, the peak of where you want to be as a scientific field. That's like the highest you can get, is to be at the level of a theory, right? Basically, you're saying there is scientific consensus. Research over time, cross-culturally, different universities has shown this thing to be true. Now, there's actually this really great documentary I show when I teach the lecture course. But I've actually had at least maybe like one student, this was years ago, one student kind of say something similar to me of, that's just a theory, or why don't they call it, like as an example in this documentary, one of these people who's like against evolution, he says, well, if it's true information, why don't they call it Darwin's, law of natural selection? Why do they call it Darwin's theory of, Any scientist will be able to explain this to you, is because a law or a rule or any of these little, they explain smaller incidences. They explain small scenarios, which in itself is in terms of a grander explanation, is kind of meaningless, right? It's when you combine all of these laws and rules together, like even in anthropology, the ones we're going to probably talk about in this class, we've got like Allen's rule, Wolff's law, Bergman's rule, like, and so you take all of these together, like these explain very particular scenarios, but when you combine them all together, you're like, oh, there's actually this whole overarching explanation that explains everything we're seeing, all of these different laws and rules. That's where you have a theory, right? So we wouldn't say, oh, Darwin's law or Darwin's, rule, because that would mean that that's only explaining a little tiny scenario. When we talk about, let's say, natural selection as an example, Darwin's idea was natural selection. When we're talking about that, that's like this grand explanation. The theory of evolution is this grander explanation. So this is why these are two completely different things. In everyday conversation, the word theory just means, oh, I have a good guess. It might be true, might not be, I don't know. Versus in science, you're like, that is, when you say theory, that is like the pinnacle of where you want to be in science. Basically, like there is scientific consensus based on thousands, if not even millions of studies that show this explanation to be the true and guiding principle of our entire field. That's a completely different idea than, oh, I have a good guess about something, right? Completely different. But people who don't maybe have a science background might not understand the terminology is a bit different, and this can cause confusion, right? So someone might say, oh, well, evolution is just a theory. When someone says that, you'll know automatically, oh, they don't really understand the terminology because what they're saying doesn't make sense. It would be the equivalent of saying, well, gravity is just a theory. Well, it is a theory. It's a scientific theory, right? So it's not the same. So if you were kind of confused about that, hopefully that explains it a little bit better. And then I think the next slide, it just kind of gives you examples of this. Like usually we don't go around saying evolutionary theory, gravitational theory, molecular theory. That's the correct terminology, but usually we're a little more relaxed with it. We would say like, oh, gravity, evolution, cells, germs, whatever. So kind of keep that in mind too. I would say this is a fairly uniquely American thing that evolution is still considered by a decent portion of the population, unfortunately, don't understand it for whatever, I'm sure different reasons, right? In a lot of other countries, even when there's like a religious, maybe there are a high amount of religious people in that population, typically this is not something that's controversial. Like I said, it's a fairly uniquely American thing in a general sense that people have an idea, or they think they don't understand this idea. And also, I'll just say that if you're thinking, well, I have a religious background, but I still want to accept science, there's nothing wrong with that. You'll find that some scientists are atheists, but I know plenty of scientists who are actually quite religious. I have one friend, actually, he's fairly religious, and I asked him about it once, like, how do you kind of navigate that? And he's like, well, I believe in God, and I believe that this creator, set up the world and our reality to abide by a certain set of rules, gravity, evolution, etc. And he's like, those two things together don't contradict each other to me, So in case you were kind of curious about that perspective, you don't have to choose one or the other, right? At all. Like I said, we can talk about that a little more in class too if you guys wanted to. But okay, perfect. We're at 33 minutes. So like I said, kind of keeping these around half hour. So that wraps that one up. And I'll see you guys on the next one.